And you've already heard some this afternoon about how optical difference imaging is becoming a powerful technique for finding tidal disruption events. So I just wanted to review a little bit how we've been finding these exciting transients in the nuclei of galaxies. Originally, the first candidates were found in archival searches of the ROSAT All-Sky survey, which was a soft X-ray survey. And since then, people have been continuing to look at X-ray observations, mostly archivally, looking for flaring events in the nuclei of galaxies. But recently, there's been a lot more effort looking at longer wavelengths. I did a lot of work with the GALEX satellite at ultraviolet wavelengths, and now there's sort of been an explosion of candidates, or at least a real increase in candidates, by taking advantage of the cadence and area and difference imaging of optical time domain surveys. And so when I made this plot before, PTF and Assassin came out with their candidates, so there are even 5 more than are shown on this plot from optical surveys. And of course, we have these 2 candidates. So this is a plot of peak luminosity versus year of publication. So of course, we have these extreme luminosity tidal disruption event candidates, which we think are associated with jetted emission, and so are a different mechanism than most of the TDE candidates on this plot here. So why are we using optical surveys? Well, it's not necessarily the best place to study tidal disruption events, since you've probably heard from some of the theoretical talks that really we expect the bulk of the energy from tidal disruption events to be emitted at soft X-ray or extreme UV wavelengths. But in fact, what's really nice about optical surveys is their spectacular cadence. And with detailed light curves, we think we can actually probe the parameters of a tidal disruption event and really start to constrain the physics of what's going on in these events, and even use them as probes of black hole mass in distant galaxies. So unfortunately, we do not have a high cadence wide field soft X-ray survey. We also don't have such a thing in the UV anymore, and so we should build such space telescopes. But in the meantime, we're doing a lot of exciting work at longer wavelengths in the optical. So the candidate that I'm going to talk about today was a result of a joint effort between the GALEX Space UV telescope and the ground-based Pan-STARRS optical time domain survey. And we did an experiment called the GALEX time domain survey, where we did co-spatial and co-temporal observations with GALEX and Pan-STARRS. And these 2 telescopes were actually quite well matched in terms of their field of view and sensitivity. And so the idea was that if you're watching the sky with GALEX and Pan-STARRS, then you can catch things that are UV bright and not always depend on smart follow-up or being able to identify sources promptly in order to get follow-up. You get the near UV observations for free. So in terms of tidal disruption events, that's actually really powerful, because we know that tidal disruption events are intrinsically hot, and they really can be distinguished from supernovae, which are a lot more common in optical time domain surveys, because supernovae do not remain hot for very long. They cool off due to their expansion quite quickly. So here is this PS110H, which we reported in 2012. This was detected as both a UV transient as well as a optical transient, and this transient was coincident with an inactive galaxy, at a redshift of 0.17, and this host galaxy had very little signs of star formation going on, and it had a mass for which you would expect a few million solar mass black hole. So it seemed like certainly a galaxy that could host a tidal disruption event. And here is the light curve from pan-stars in the blue, cyan, green, and orange, and GALEX in the magenta. And you can see that it has this very nice, smooth shape, a rise, and then a power law decay that's actually quite similar to the t to the minus 5/3 power law that you expect for a fallback accretion in a tidal disruption event. And in our first paper, we fit the models that were available from Lodato et al. 2009, and we found a remarkable easy fit just by taking these models and scaling them the x-axis to fit the single band data. And just from this fit, you can get a constraint on the black hole mass of 2 million times the mass of the sun, but now you still have an uncertainty on the black hole mass because the mass and radius of the star disrupted is unknown. So the question is, before we get too excited, can we really trust this black hole mass? Well, there are a lot of details that have emerged as theorists have been thinking about this more carefully, and there are some basic issues where the most simplistic theory of this fallback accretion forming a disk around the tidal, with a size close to the tidal disruption radius around the black hole, doesn't really fit our observations. And so if you're going to trust this black hole mass first, you need to think about if we understand what type of star was disrupted. I'm going to talk about the spectroscopic properties in a second, but you're going to get a different black hole mass depending on whether or not you think this was a helium-rich core of a stripped red giant, for example, or if you think it was just a main sequence star. And then there's a lot of interesting questions of why is it that these UV and optical light curves are following the fallback rate linearly. You would expect band effects due to cooling of the radiation with time, and you would also expect much higher temperatures than we observed. We observed a temperature of 30,000 degrees Kelvin, or 30 to 50,000 degrees Kelvin. So there have been some ideas in literature of how to get around these problems. But we recently, or last summer, we obtained UV observations and optical observations of PS110JH with Hubble. And what's really neat is when you look now with Hubble, in the optical you basically just see the host galaxy light, but in the UV you see a point source, and that's shown with the magenta contours. And with careful astrometric registering of reference stars in the field, you can register the optical and UV images, and the cyan circle shows the 1 sigma uncertainty on the centroid of that magenta point source in the UV, and you can see that it's coincident with the nucleus of the host galaxy. So not only is this source still shining in the UV, but it is definitively within the center of the galaxy by 66 parsecs. So it is a nuclear source, and it's still shining in the UV. And so now if we look at its UV flux, it's remarkably continuing to follow these fallback rate models. So now I'm showing two models, one from Lodato et al. 2009, and one from a suite of models from Guillochon et al. 2013. And the Guillochon models fit some of the structure in the later portion of the light curve a little better than Lodato light curve, Lodato model. But you can see that basically the UV is continuing to decline close to these fallback rates, and consistent with a t to the minus 5/3 power law. And this is 3 years later after the peak. So I mentioned the nature of the star, so there's a lot of interesting information in the spectroscopy of this event. And originally, when we published our spectra, we didn't have a very good late-time spectrum of the host galaxy. It still had some transient emission superimposed on it. So we used a synthetic galaxy template to isolate the emission from PS110JH. Well, now we have a better high signal to noise late-time host spectrum. So now we do a direct subtraction. We basically still get the same result. We still see these broad helium lines, these broad helium-2 lines, and as well as a hot blue continuum. And one thing I wanted to note is that with this late-time host spectrum, we do measure the equivalent width of H delta, and I didn't get to hear Yair's talk, but for this galaxy, we don't measure an equivalent width for H delta strong enough to be classified as an E+A galaxy. So this may not be a rare post-starburst, but may be a more normal elliptical galaxy, early type galaxy. So I just wanted to focus a little bit more on these helium lines, because one of the most surprising things about the spectrum is not so much that we detect helium, but that we don't detect H-alpha. And so shown on the left is the broad helium line with a full width half max of 9,000 or so kilometers per second. And I'm showing the Gaussian fit to that line in green. And then the dashed lines show the full width half max of the line in velocity space. So one neat thing is you do see some excess in the blue wing of the line, and but even more interesting is the fact that when we look over at the velocity region near H alpha, we really don't see anything. Now I've hashed a region with red dots of where the telluric band correction is, so where you have to be a little bit cautious. But we really don't see a line. But I did integrate the flux between the dashed lines for both lines and took their ratio, and I get a ratio of 4.7 plus or minus 1.0. So I kind of use that as the upper limit or the lower limit on the helium-2 to H-alpha ratio. So we really don't see any broad H-alpha, and it's at least greater than 5. And this is very interesting because this is, you're going to hear more from Nathan Roth. We interpreted this extreme ratio as due to a lack of hydrogen in the star, but perhaps there are some photoionization conditions in a thick envelope surrounding a tidal disruption event that could cause such extreme ratios. But this, we really don't see any H-alpha to a limit of helium-2 to H-alpha greater than 5. Okay, so my conclusions, our HST observations of PS110JH confirmed that the flare was nuclear. The late time flux follows the t to the minus 5/3 fallback rate, 1,250 rest frame days after the peak. We confirmed the helium-2 to H-alpha greater than 5 ratio measured in our first paper with better host subtraction, and we do not classify the host galaxy as an E+A, as claimed in our Kavi et al. 2014. So the implications, PS110JH really cannot be a supernova because it's maintaining a very bright UV luminosity over a long period of time, and you really cannot reproduce that with a supernova. And we really don't think it was a microlensing event. Its light curve doesn't look like one, and also the fact that it is nuclear disfavors a microlensing event which would occur from a random star in a unseen foreground lensing galaxy. We still show the fact that the UV flux density still follows what we would assume would be the bolometric luminosity and the decline of the mass accretion rate, and therefore you can't have band effects that would change the behavior in the UV and optical bands compared to the bolometric luminosity. So we need some sort of fixed SED, and I think there are going to be a lot of talks giving ideas on how to keep your spectral evolution, how to keep your temperature fixed. We also need efficient circularization because we seem to rapidly be following the mass accretion rate without any delays in the radiative output. And then finally, the suppressed hydrogen emission could be the signature of the helium-rich chemical composition of the disrupted star. So perhaps this was analogous to supernovae. This would be a stripped tidal disruption event so that the star was already lacking its hydrogen envelope. But there's just recently, hot off the presses from Roth et al., some calculations which show some conditions in which you can get very extreme helium to H-alpha ratios with these optically thick reprocessing envelopes. So I look forward to learning more about that and figuring out what is the best explanation for our object. Thank you.
How do you technically do this?
That's a good question.
Thank you, Suvi. Can you hear me?
Yes, I can hear you.
We're going to take some questions.
Okay. Hi.
So, hi, Suvi. Question. Richard?
Hi, Suvi.
Hi.
What will it be reprocessing after 4 years now? If it's a big reprocessing screen, what exactly will there be in the middle which is producing this emission that it's getting reprocessed? Because you didn't see X-rays after 1 year.
So in the Roth model, which obviously I just read because it came out last week, the idea was that you could form this reprocessing envelope from the debris, and I guess you must be able, so in our case we would have to form it quickly because we see this helium, we see this hydrogen emission suppression at 22 days before peak. But then the idea, I think, in the model is that material from this envelope could be draining out over time. I don't think you would have a new source of material. But I think this envelope, and you'll have to ask the authors, but I think this envelope could persist for a while. But that might be also, I think what you're bringing up is that perhaps the long-term persistence of this emission could potentially constrain the model if it's hard to keep that envelope steady. Is that what you're implying?
No, I was really talking about the primary source of radiation that this envelope is reprocessing. Where is that coming from?
The primary source is continued fallback, so it's the light curve is following the rate at which you'd expect material to be continuing to return to pericenter from the initial disruption.
But then we'd see X-rays though, wouldn't we?
Well, we never saw X-rays, so when we looked with Chandra close to the peak, we did not detect any X-ray radiation, but that was consistent with a soft temperature. So basically a temperature a little bit less than 10 to the 5th Kelvin. So we didn't see any initial X-ray photons, and I don't see any spectral evolution in the UV, but it's possible you could look for X-ray emission now, but I don't know, I don't have a good reason to think we would see X-ray emission now.
Tiffany?
Just directly related to that. So I guess the key thing is that helium-2, in order to create the ion, it has its ionization potential in sub X in order to produce a strong helium-2 emission line, you do need strong soft X-rays. So why are these not seen?
Oh, okay, so we do get a lower limit to the temperature for how many photons you need to photoionize helium, and that is still safe, or it's still consistent with the upper limit on the temperature we get from the Chandra observation. So there's still enough extreme UV photons around to ionize the helium. And remember that Chandra isn't the ideal telescope because its soft X-ray sensitivity isn't that great. So, you know, only being sensitive down to 0.3 keV or so isn't the best for probing the soft X-ray.
Sure.
Quick question, did I understand right? Are yours optics, the helium-2 had an asymmetry with broad to the red, whereas this one was broad to the blue, is that right?
No, so it's a little bit confusing because they're being shown at different scales, but I had this one plot where they're on top of each other, and it seems to be blue shifted, so it seems to be asymmetric with the tail, a longer tail to the red, but the peak is blue shifted. So what she's, yeah, the blue axis that Subi mentioned is where the peak would be, but hers had an additional component on top of that.
Nick?
Hi, Subi. Is the lead time optical non-detection consistent with optical also following T to the minus 5/3 and just falling below the host galaxy flux? Or would it need
So it's really hard to do a optical non-detection because you know, with HST we have just this one epoch, and I don't see any morphological evidence for a point source in the center of the galaxy still shining in the optical, and based on the decline that you see in the UV, you wouldn't expect to detect any significant emission in HST. But in order to actually carefully do that, you'd need a second epoch, second late time epoch to do a difference image with the HST imaging. But based on how faint you expect the optical to be anyway, you do not expect to see it in the HST image clearly above the host.
One last question, someone? Oh.
Any signs of release of mode in the HST image?
No, it can be described quite well with the de Vaucouleurs profile. There's no evidence of disturbed morphology.
Okay, let's thank Suvi again. Thank you, Suvi.
Thank you.
Is the other one not working? You can try it again. Try. Oh, I don't know what that is. Try that. And if not, try this. Well,
wait a second, maybe.
can start. Right.
הנה, עכשיו זה עובד. הוא עובד.
לא, הוא נדלק גם קודם.
כן.
לא זו הייתה הבעיה. Now we also left it. Right, this one.
I do.
הוצאה לא זהירה של הקונקטור שעוברת איזה פינישר, השאלה אם הוא יכול פשוט להביא קונקטור על כל הכבל, אז כבל אחר.
מה אתם חושבים שהקונקטור לא טוב?
תראה, זה הבד, ואז יש לך עוד קונקטור?
יש את הקונקטור שלך, לא?
לא, לא, זה לא, זה ניסיון.
אבל אתם רוצים להתחבר עם זה?
לא משנה,
מה שעובד.
שום דבר לא עובד, וגם המסך לא עובד.
Tal, you got any good jokes?
No, don't. Trust me, you don't want to do it.
Okay, we should just... אולי נמשיך למסכים פשוט. אפשר להחזיר את המסך הזה?
Okay, you're on 2 screens, but not 3. We can work with this.
All right, yeah, I'll do my best. All right, good morning or good afternoon or good evening. I really have no idea what time it actually is now, but thanks to the organizers for putting together this really nice workshop. I'm very excited to be here. I'm going to talk about a program I've been leading with HST to obtain UV spectroscopy of tidal disruption events. We've had some really nice introductions, even though I've only been here for the last couple of talks to sort of motivate this work. Yair showed this plot earlier showing that there's this continuum of hydrogen to helium ratios in the optical spectra of TDEs. There are a variety of different possible explanations for why that might be. You heard from Suvi that maybe this is telling us something about the star that's being disrupted, that it's just a helium core lacking some kind of hydrogen envelope. And she also alluded to Nathan's paper here and also some work that James has done saying that maybe what's going on is we're actually observing photoionization effects in some kind of larger reprocessing layer, and that can actually mask and give you, depending on where this reprocessing layer is happening, you can get actually quite large ratios of helium to hydrogen here. These are for 3 different radii for this. So Nathan's going to talk about that much more in depth and intelligently than I can, I think, either tomorrow or the next day. So why would you want to actually get UV spectra of these things? I'm a very simple-minded guy. I like to go where the flux is. This is the composite spectrum of a quasar from about 1,000 quasars from SDSS. You can see the spectral energy distribution in the optical is relatively flat. It turns over about 4,000 or 5,000 angstroms, and most of the flux is coming out here in the UV. So I like to look where the signal to noise is. You can also see that there are a bunch of features. If you're looking in the optical, you're pretty limited to the Balmer series, maybe some forbidden narrow oxygen lines, and of course these helium-2 lines that we've seen. But there are many magnesium-2 for semi-forbidden carbon-3, carbon-4, Lyman alpha, neon-5. There are lots more atomic features if you go look in the ultraviolet. And in fact, there is some evidence in at least one TDE that maybe there's some interesting behavior going on here. This is PS111AF from a paper by Ryan Chornock, where you see in this spectrum at 24 days, there's this quite broad feature that is not there at 5 days, and it's clearly not there in the host spectrum taken a few hundred days afterwards. So there's this transient broad feature, conceivably where you might expect to see magnesium-2 in the spectrum. It's blue shifted maybe by, I think, about 5,000 kilometers a second, so it's not exactly at 2,800 angstroms. But if you've ever done sort of quasar business, temperature, density, velocity diagnostics, looking in the UV is a very natural place. And of course, when we project forward down the road, when we think about the TDEs that LSST is going to be discovering, because it's so sensitive, it's going to be finding these at much larger redshifts than things like Assassin. So if we want to look in the sort of observed optical bandpass for LSST, it's actually going to be rest frame ultraviolet emission. So we really want to understand what's going on in the rest frame UV. So, so far we've triggered this on 3 sources. We heard about 2 of these from Thomas's talk. Assassin 14Li, which is at a distance of 90 megaparsecs. Assassin 15OI, redshift of about 0.048 or 0.049. And I'll talk very briefly about IPTF 15AF, slightly larger redshift than this. For these purposes, you can essentially treat it as a clone of Pan-STARRS 1 10JH, but with a slightly hotter black body temperature. And we're getting, STIS spectra from, let's say, 1150 to 3200 angstroms or so in the observer frame. Okay, what do these spectra look like? I should say this is all a work in progress. So I'm going to be kind of going through this on the fly. Here is our spectrum of Assassin 14Li. So again, to give you sort of the main numbers, distance of about 90 parsecs, peak luminosity a bit shy of 10 to the 44 ergs per second. Radiated energy, I thought it was about 7 by 10 to the 51. Thomas, you can correct me if that's wrong. Okay, so this is integrated radiative energy, and the SED is actually quite strange. You see this double black body with an optical best fit temperature of about 35,000, and then additional component in the X-rays where it's shining at 10 to the 5th. Okay, so let me give you some guidance to sort of walk you through what you see here in case you don't think about UV spectra a tremendous amount. This is the same plot that I showed earlier, composite quasar spectrum from SDSS, magnesium-2, semi-forbidden carbon-3, going up to carbon-4, silicon-4, and Lyman alpha neon-5 up there. Okay, a couple things are immediately apparent if you just look at this very briefly. First of all, there's essentially nothing going on in the near ultraviolet, right? Just continuum. All of the stuff that we see sort of going on here at what we'll call far ultraviolet wavelengths. Also, you can see that this thing is quite hot. So this was taken a couple months after discovery by Assassin. This is the same composite spectrum that I showed you before, where it was sort of zooming up in the blue. And this guy is even hotter than a sort of typical quasar spectrum down at these sort of 1500 angstrom wavelengths. So let's zoom in on a couple features of interest here. This is the magnesium-2, which I'm going to take as representative as sort of low ionization lines. Magnesium-2, carbon-3, silicon-2, carbon-2, these kind of features. Assassin 14Li in black, quasar shown in blue here. You see this nice sort of emission feature in the quasar. There's nothing like that in Assassin 14Li. You see this sort of absorption right here at minus 6,000. This is just absorption from magnesium-2 in the Milky Way. It's essentially redshift of 0. There's no absorption or emission from any low ionization features in Assassin 14Li. And that will actually be a trend as we see that in some of the other objects. Yes?
You're only showing velocities here to 10,000, it looks like. Wasn't 11 AF at like 15,000?
Yes.
So there's no absorption even at very high velocity.
So you can walk this out. This plot before was showing sort of from here to here. You can walk it out all the way down to, as high as you want to go. Strictly, smooth continuum, redward of 2,000 angstroms. Okay, high velocity lines. A lot more sort of interesting stuff going on here. So this is zooming in on what I think is helium-2. It's pretty likely, I'd say, identification because we see this in the optical spectrum. Carbon-4, nice strong line that we see in lots of quasars. This, I honestly don't know what this feature is. There's something very weak in quasar spectrum corresponding to semi-forbidden nitrogen-4. And we see in this very strong nitrogen-5 as well. So I think that's a plausible identification, but honestly, I don't know for sure. So you can see broad emission lines, full width, half maximum, maybe like 5,000 kilometers a second. Pretty good speeds. Also, strong, relatively narrow absorption lines. So this is carbon-4 from the Milky Way. This is carbon-4 at the, in the host galaxy. If you remember from the previous spectrum, the magnesium-2 was, comparable strength to the carbon-4 in the Milky Way. No magnesium-2, but very strong carbon-4 in the host galaxy. And in fact, if you look at, we have pretty accurate 0-point redshifts for this carbon-4. And if you look, it's hard to see at this stretch, but this line right here is actually blue shifted by a velocity of about 80 to 100 kilometers a second. Okay? And that might make you think of something interesting, because in fact, something very similar was seen in the X-ray spectrum for this source. So these are high-resolution X-ray spectra taken by XMM on the left and Chandra high-resolution gratings on the right, slightly lower signal-to-noise. You can see that there are absorption features from very highly ionized material. This is oxygen 7 or 8, 6 or 7 on the left. Argon 14, argon 13. This is really, hot stuff in order to get this kind of ionized material. And these lines are blue shifted again by speeds of somewhere between 100 to 300 kilometers a second. And in fact, that blue shift sort of changes as a function of time. So the optical and the X-ray are both telling us that there's some kind of low velocity outflow, material circularizing around. I mean, it can't be a true outflow because these speeds are not nearly high enough to escape the potential well of this black hole at any reasonable distance away from where they might be occurring. But there's some kind of stuff moving away, these sort of low speeds that are probed by the X-rays and by the rest frame UV lines. Okay, next. IPTF 15AF. So I mentioned that, for these purposes, we're going to consider this more or less a clone of PS1 10JH. This is a spectrum around maximum light, rest wavelength. You see from 15 PTF, 15AF, which is different from PS1 11AF, which is extremely confusing and also very unlikely statistically, but such is life. You can see this broad helium-2 feature that we use to classify these things now, whereas really nothing convincing going on here at H-alpha. The only real difference in their evolution is that the black body temperature of PTF 15AF is quite hot at early times. Here's what the spectra look like. I still am trying to wrap my head around what's going on here. Again, sort of nothing going on at this sort of low ionization lines. No magnesium-2, no carbon-3, nothing like that. However, now you see, instead of just emission features, you see these sort of broad lines down here at the blue end of the spectrum. This is plausible. This is some kind of carbon-4. This corresponds to where we see carbon-4. This is where Lyman alpha is in the rest frame, silicon-4. They look sort of Peace Cygni-like. I don't know. Depends on exactly what you assume for what the continuum looks like. They're somewhat blue shifted relative to where the peak of the emission or the sort of 0 point should be for this galaxy. And they're quite broad. Velocities are 7,000, 8,000 kilometers a second. So again, there's evidence in this case for even higher velocity outflows, but only from this really highly ionized material. You really do need these really hot temperatures to get you looking at this. Okay, last, Assassin 15OI. Shown here in black. Can sort of, this is just due to the air glow lines. You can ignore this absorption feature. Repeating broken record here, nothing going on in the near UV. In the far UV, plausibly carbon-4. Hard to make a strong identification. Plausibly Lyman alpha. Again, you see something that looks, particularly if you look at this as some kind of continuum level, P Cygni-ish like. I wouldn't bet my life on that. These are very broad features in sort of the high ionization lines and nothing going on in the low ionization lines. Okay, so let me try to summarize what we're learning from these things. And we're sort of going through now and trying to do the actual detailed cloudy-like modeling. It's not sort of the ideal approach because these things are perhaps not as static as cloudy might assume. But we can say, all right, strong blue continuum all the way out to Lyman alpha, bluer than seen in sort of this canonical quasar spectrum. Lack of low ionization lines in emission and absorption. Nothing that we can see points to the fact that there's Mg2 in any of these spectra. It is completely unlike normal sight lines to quasars. Lots of stuff going on, high ionization features, carbon-4, silicon-4, definitely an emission, possibly an absorption. See this sort of narrow blue shifted absorption from Assassin 14Li. It's very consistent with what we see in the X-rays. Possible P Cygni lines, again, pointing to some kind of outflow stuff. And there's possible detection of Lyman alpha emission in two of these sources that don't show H alpha emission. Okay? This could be some way to distinguish, I guess that one's out again. Okay. This could be one way to distinguish this sort of, helium core versus hydrogen envelope thing, is looking for Lyman alpha. Unfortunately, there are lots of other features going on sort of at those kind of wavelengths. So my take-home message, there are extremely complex photoionization conditions going on in these sources. They're entirely unlike what we see in quasars and really are going to require sort of detailed photoionization modeling if we want to understand the sort of basic physics, the temperature, the density of this material, the distance from the emitting source. Okay, how much time do I have left? Great. As a NASA employee, whenever you give a talk, you are required to pitch a future mission, sort of part of your job. So, if we want to find more of these things, obviously the Assassin survey is doing a great job of finding bright nearby sources. But coming back to this question of, where's the bulk of the emission coming out, looking in the UV is a very natural place to do that. So I've been putting together a project to try to do this, a wide field UV transient survey from a CubeSat platform. If you haven't heard of a CubeSat before, CubeSat is a type of miniaturized space satellite for space research, has a volume of 10 centimeters on a side, and a mass, very strong mass and power requirements. The reason why this is an attractive option is because by fixing the form factor, commercial companies will make sort of standard spacecraft parts like communication, power, computing, all the sort of normal things that you need to operate any spacecraft, and you can buy them for relatively cheaply. And because they're relatively compact and standardized, you can fly them as sort of, if there's extra space in other bigger missions that are going up there. So this is just to show you how most of them are currently being deployed right now. Since most of the cargo that's going up to space is going to the International Space Station, they have these sort of robotic arms that kind of push these things out of the ISS. And this is actually the first two satellites from Planet Labs, if you've ever heard of them. They're doing